pleasure to welcome you to the University of Exeter, and which is having an important week this week with various conferences and meetings going on around climate change and tipping points and things which we spoke a little bit about last night. And important for us is this meeting here, a very international collective trying to understand the innovation that's needed to deliver a zero carbon economy as soon as we possibly can do, and recognizing the opportunity as well as the challenges that we're all facing. So it's great that you're all here. Really looking forward to the sort of interdisciplinary panels that we're going to have and the discussions that that's going to form, the connections that you're all going to make, and I know that's already started, and the follow-on conversations that you're likely to have throughout these 2 days and beyond it as well. So that's the value of us all coming together. So I'm going to hand over to Amanda Ellis. She's going to say a few things, and then we're going to crack on with our meeting. Please, Amanda.
I love the crack on. Well, aloha, good morning, everybody. Wonderful to see you all. Very excited for the next couple of days. You probably are all very aware that the IPCC estimates we need to take 10 gigatons of carbon out of the atmosphere per annum by 2050. So no pressure, everybody. And we're really delighted this morning to have as our keynote speaker the person we call the father of direct air capture, Klaus Lackner, who is the founding professor at the Center for Negative Carbon Emissions at Arizona State University. So this is now part of a much bigger Global Futures Lab, and we're delighted to have a number of people from the lab here with us, and Matt Green, who's now running the lab for Klaus. So back in 1999, Klaus was the first person to actually suggest that it was possible to technically capture carbon dioxide in the context of carbon management. And he was previously director of the Lenfest Center for Sustainable Energy at Columbia University. We are very excited to have him now with us at ASU. And Klaus is also a fellow of the American Association for the Advancement of Science, and was recognized for contributing to the 2007 Nobel Peace Prize for the IPCC. Klaus, we're so delighted to have you with us. Take it away. Crack on, as will be the motto of the day.
Well, thank you for having me here. It's an honor. It's not the first time I'm doing this. And maybe I need to stop it because I feel like a broken record. So because it's moving very slowly forward. So I want to talk broadly about carbon management and the carbon budget. But given that I am very much involved in direct air capture, I certainly will have a few things to say directly to that topic so that we can see how that fits into the larger picture. First of all, it should by now be clear, and I think the IPCC and the Paris conference in 2015 actually made it clear, we are on a budget, right? The fossil carbon, I think the simplest way to think about it is to just step back. The fossil carbon enters the mobile carbon pool, and we can argue what exactly is the mobile carbon pool. In my mind, it's the atmosphere, at least the top parts of the ocean, and a vast part of the biosphere. Now, there are some parts which are more mobile than others. If you have a 300-year-old tree, the trunk of that lasts 300 years, but the leaves are coming and going on a yearly basis. As a matter of fact, the biosphere pulls roughly a quarter of the CO2 out of the atmosphere every year and then spits it back out. So these are tightly connected reservoirs, and that's what we keep entering things in. And if you look at it, at current rate, it takes us about 60 years to add enough CO2, put out enough CO2 to match the amount which was in the atmosphere in pre-industrial times. So that is our challenge, right? On the other hand, don't worry about it. It will go away. It's on geological time scales, but those are 100,000 years or at least tens of thousands of years. And so for all practical purposes to humans, we constantly take a carbon loan, and we are not really paying it back. Our payback schedule is insignificant on that scale. So we have to figure out how much of a loan we can take before we turn out not to be creditworthy. And we could make the case, like Jim Hansen said, 350 ppm was probably not a bad place to be. If nothing else, he made actually the statement, at 350 ppm, you won't fall into an ice age anymore. And maybe that's not a bad outcome. But how about 450 ppm or 500 ppm? And if you simply extrapolate, and I showed you this last year, current trends, we are at about 800-900 ppm by the end of the century. By the way, this is an advance because I have played this game since the early 90s. And back then, if I extrapolated out, I would have crossed 1,000. So we have done a little bit since. So, but that now basically says that we are in an overshoot, and we should start thinking about the problem differently. We used to think about, we need to hold, and I can quote you and find you exact quotes about it, we need to hold emissions constant. No, we have to go to zero. And if we overshot, which I argue we have at least started, we may be having a little bit more, but inertia is enough, we will overshoot, right? Then we have to take it back. And where the target is, we don't really know. And if it's 1.5 degrees, well, we just bumped into that. If it's 2 degrees, we have another decade or so, or maybe 2 before we actually cross that line. But given the inertia in the system we have, there's no practical way. And I would argue we are committed to 500 ppm, no matter what we do. If we are really, really good at it, we might turn the ship around right at that time. And as I said before, if Jim Hansen is right, and if you simply take the Rio Agreement from 1992, which said we should not put harmful amount of greenhouse gases into the atmosphere, we may have well overshot that already. So we need to figure that out. And I would argue, if you're in the business of negative carbon emissions, you should rejoice, sadly, because the business is going to get a lot bigger because the current politics is slowing us down, right? And that is horrible and dramatic, but the net result is our overshoot will get much bigger. I think we just committed to another decade we could have had avoided. And that's because we in the US have decided that climate change is a hoax. We abandoned Paris. And if the second largest player says this, you can be assured many others will say too, if they don't do it, we will not do it either. So I hope that we don't do that. But I think the business for negative emissions just got another 30 ppm added to its challenge. And to make things worse, we have a number of carbon removal technologies. Everybody here in the room knows that. Let me be aggressive about it and say, none of us really can do it at this point. Either we are too small to get to the full scale, our environmental footprint at full scale would be horrible, or like in the case of direct air capture, our energy demand is too ridiculously high still, and our cost is 10 times larger than we need. So we are standing there and say, well, the technology sort of exists, but it's not yet ready for prime time. And so we have to figure out how to bridge that gap somehow or another. And I always hear, well, there's no silver bullet, we need to do everything. I'm not sure whether there's no silver bullet, but we don't know. And the problem is we could all in our hearts say, well, you know, my technology is going to be that silver bullet. But if I were a policymaker, I wouldn't trust any of us and say, we need to make everything work, whether one of them is a silver bullet or not, right? Because we don't know, and we will not know until it's way too late. So we need to move forward as fast as we can. And we have, of course, two big options. Either we completely eliminate fossil fuels, or we neutralize their waste. And I think, again, because we need energy, we got to figure out how to do both. So what's at stake? I would argue it's about equitable access to a good standard of living. And that was what got me in the early 1990s. What bothered me is that we, the rich countries, and we are doing this still today, we, the rich countries, I can fly from Denver to here and have a good time talking to you all. But developing countries get told, well, tough. We ate 11 slices of that 12-slice pizza, and we now tell you that you can't have the last piece because we needed to. So we got to figure out how to be equitable to everybody. And that does not just mean today's generation, also future generations. So when it comes to pollution, we are not allowed to just dump it. My fear is we will always do some damage to future generations because we don't know better. But in this case, we know better, and therefore we don't have the right to do that, right? And we need access to a clean and stable environment. And that's what we are ruining with the energy we are consuming right now, at least in the way we are doing it. And we are risking food and water supplies for people, right, by changing the climate in an ununderstood way. And ultimately, all of this requires stability for a modern society. And if you pull the rug on food or energy or economic development, you will see political instability, which comes with this. What we really need, and this is where I came in, I didn't come into this as the environmentalist who said, I want to fix the climate. I came in, we need energy, and we need to figure out how to have access to energy, because if we don't, we are in big trouble. And I think we have a tendency to say, well, just use less energy, but then look at what happened when the Ukraine war started, right? Energy prices went way up because everybody said, well, we need it anyhow. So we got to figure out how to do it right. And part of that is to abandon fossil fuels. And part of it is, to the extent that we can't, we need to make it work. So photovoltaic power, I do think, will challenge fossil energy in a good competition. And I think it is actually absolutely remarkable. If I look at the chemical energy in natural gas, it is more expensive than the electricity, the raw electricity coming off a solar panel. Now, neither one is yet consumer electricity, but at the starting point, we now have something that's cheaper than natural gas. Still not cheaper than coal, but cheaper than natural gas. And that is an enormous change in how things work, right? And we argue, if we really want it at a full scale, we need to store it on the hour basis. That sounds like batteries, but we also need to do it on a seasonal basis, because if you tell people they can't use the energy in the winter because it's only sunny in the summer, you have a problem. So we need to figure out how to make liquid fuels out of that energy and convert it, and I'll come back to that by the end. Coming back to the fossil carbon, I think of that carbon as a waste management issue. We create that carbon, we extract its energy, and then we say, well, we don't know what to do with the leftover CO2. By the way, we make more CO2 than we make concrete and aggregate. Actually, more than sand and aggregate. Not much more, but more. So it's a waste management problem. And by the way, if you think of it as a waste management problem, you now may start thinking about recycling, because cleaning up that waste will cost you money. And maybe you wanted to use less to avoid that cost. Or maybe you can do something useful with this particular ton of carbon dioxide. So by all means, go ahead and do it, right? And what's different with CO2 is that is a waste which is global. And by the way, that 1 ton coming out doesn't do any local damage. What it does is it raises the tide everywhere. So you can actually solve this waste problem, not at the moment it's emitted, but by simply balancing the books. And I'm arguing we could do that. And of course, then carbon recycling will be driven because it works. But we need to scale up to work on the right scale. And you heard just 10 gigatons, and I believe these are 10 gigatons of CO2 because I read it too. But I'm arguing that's actually a small number. And I give you 3 ways to end up with 40 gigatons per year. First one is roughly, and it's actually 36 or 37, roughly we are putting out 40 gigatons of CO2 a year. If you simply take the 2% annual growth in energy consumption we had and you forward 80 years, you notice I'm getting old. I did this in 2020. By the end of the century, you are 5 times larger than we are today. So if you manage to get 80% of the carbon intensity out of the system, you should anticipate that by the end of the century, we are back at 40 gigatons a year, because you grew to 200 gigatons if you hadn't done anything. So bottom line is, I have now 2 ways to get it. The third way is to say, we got to clean up and we are 100 ppm over, and I give you 40 years to solve the problem. 40 years of mopping up CO2 to get 100 ppm back down is about 40 gigatons a year. You see this instantly because we are going up by roughly 2.5 ppm a year. So if you want to go in the opposite direction, you have to unemit, reabsorb roughly as much as we are putting out. And then the question is, how much time do we have? Well, if I were Jim Hansen, I would tell you we have no time. 10 years is probably not practical, although I had this interesting discussion, unfortunately involving Climeworks, where somebody pointed out, you know, in 2008, you started with 2009, and so did the iPhone. Why doesn't everybody have an air capture device? What is different about the technologies? And I would argue small and mass-produced can get you a long way. There was a very interesting paper by Dan Sarowitz and Dick Nelson, who was at Columbia in 2008, which I nearly missed because it talked about 3 rules for technological fixes. And the technologies they were fixing on the first page was vaccination, which is sort of ironic in hindsight, as an example of clearly this works and is accepted, and how to teach reading, where people are fighting because it's sort of spongy, whether you should do sight reading or spelling out. And then on the last page, he says, why don't we do this for direct air capture? But the point he makes is the technology must largely embody the cause and effect. And I think with CDR, we have that, right? If you put a ton away, well, you clearly solve the problem. There's a very direct connection, right? And that's the second point. And the third point says, you have to have a plausible path to get there via research. And I would argue the last 10 years have shown that we can. So we better figure out how to make that work. And I would argue if you want to succeed, either with direct air capture or with any CDR, I think you need first and foremost a clear transition path. And that means, most importantly, public acceptance. If the public doesn't want it, we are not going to get it. Right? And right now, it's horrible. I actually drove along here last night because I visited a friend, and I saw on the back of a sign, climate change, a scam to control you. Right? If that's the attitude, we are never getting anywhere. Right? Early applications are necessary. And I think there's a lot of little stuff which doesn't solve the climate, but proves that the technologies work and allows us to lower the cost of those technologies. If you give CO2 to greenhouses, if you captured it from the air, you're not solving the climate. But you may lower the cost of CO2 capture from $1,000 to $100. And now you can solve climate change. And you have to make some case that the technology can actually grow. Now, feeding greenhouses will never be big enough and not solve the problem. But having the machines and say, I could have 100 million of them is a fair argument. If you come to the question, can other technologies do this? I think you always have to ask, can you get a big chunk of the problem solved? There's nothing wrong with having technologies which sort of ride on the side, which can never get big enough, but could help in the overall process. But from a policy perspective, you want to get those who can actually get big enough. Ultimately, you need market pull. Maybe I have too much of a liberal streak there that I'm saying markets are powerful, but these markets require regulations. And I used to live in Phoenix a long time, and I paid Waste Management, the company, a monthly fee, right? And the reason I did, not only I agree with it, but I also had no choice. I had a choice between them and 3 other companies, but I couldn't dig a hole in the backyard and put the waste in there. It's regulated. And by the way, they are also regulated, and this is where Stephanie will come in later, because how do I know that they don't drive around the corner and just dump it in a ravine, right? So somebody has to deal with that market, and then you need fast growth, as we just said. If it takes you 70 years to figure this out, we are too late. And I would argue scaling by numbers has historically proved much more efficient than scaling in size. And that's where the iPhone won. And then you have technical advances, which we absolutely need. That technology is truly too expensive right now, most of them, and we have to figure this out. Now, my point is, these things you can write down and you can work on every single one of them. But they interact. If the technology gets cheaper, the acceptance becomes easier, right? On the other hand, the technology doesn't get cheaper if it isn't accepted. The same with market pull. We can have some voluntary action here and there that makes us feel good and gets us started. But at the end of the day, if we want to get 10 gigatons or 40 gigatons back every year, you cannot do this without government saying this must be done. So we need to figure that out. Now, what I think would help with public acceptance is I think we need to figure out how to make it affordable. And I would argue, currently people bandy numbers like $1,000 a ton. I think that's too much. $100 a ton, I can make the case. If instead of solving the problem, we simply take the carbon economy as it is and raise prices so that we effectively absorb $100 a ton of CO2, the oil prices are still within the variations we have seen. Electricity prices are still within the market prices in the various states in the US. If I compare North Dakota or South Dakota to California, that price difference is vastly larger. And by the way, California, with the high price, is the richer of the two. But the variance is much, much larger than the $100. If you put another zero on it, it'll stifle the world's economy. It must not be inconvenient. You see this in the electric car discussion. You see it everywhere. If you ask too much from people, they will tell you it's a hoax. And that to me means no lifestyle changes. It's also an admonition to all of us. We really like the idea, maybe we can kill fossil fuel, or maybe we can force people to have the right lifestyle. The moment you do that, you are coupling two problems, which both may need a solution. But by coupling them, you guarantee you won't get either. And that's why I tend to say, let's just solve this problem. And then, yes, there are other problems in the world. And it's nice to ride on the coattails of another problem. But if too many people ride on the coattails, you're not going anywhere. And that's what you are seeing happening with climate right now. You need minimal side effects that will challenge many of the CDR technologies, because at 40 gigatons, we are large. And if we make one move, we are dumping a whole lot of stuff somewhere or another place, and we can't have a solution to the problem which solves the climate, but at the same time creates all sorts of other problems. And this does not just apply to fossil fuels. To give you my favorite pet peeve right now, everybody talks about perovskites making solar panels much more efficient. Now, they haven't quite figured it out yet, but every perovskite which looks promising is a lead perovskite. Are you really wanting to cover the desert in lead? And then in 30 years from now, have a cleanup problem where you have to fix this? I'd rather take the hit in efficiency and have simple silicon. The worst case it burns to is quartz, right? But this is a human trait, I think. We have always a tendency to just push those problems away, don't deal with them, and worry about it later. The benefits need to be understood and directly related to action. And this is sort of where Sarowitz and Nelson came in with their state. It also means you have to have a clear narrative. You have to tell people what it's about, right? And if you say it's about killing the oil companies, well, then the oil companies will push back very, very hard. Maybe it is about cleaning up, right? And it needs credible accountability. We are not going to do this if nobody knows whether it really got done. And I would argue, and I'll come back to this in a second, that if you demand that we can trace all of this through the economy, the Soviets tried and failed. We cannot track things through. And ultimately, I don't want to belabor that point, but it's actually important. It must be fair. If some people feel they are the biggest losers, the person here who thinks they get control, the oil company who is forced into bankruptcy, if people feel that they get the raw end of this deal unfairly, they will push back and they will get traction because they are viewed unfairly. So a market pull has to come from regulations, and I don't want to belabor it too much, but I would point out all markets are regulated, not always in demand, but I bought a house And I rely on the fact that no four big guys with baseball bats come in and say, now it's mine, right? That is a regulation. The right to property is a regulation as well. And so here we need a regulation which says you cannot dump waste. And we need to, of course, certify that it got done. Here's a very simple thing, and Stephanie will probably tell you more about it. Our view is that this is a proposal, don't try to do it at the end of long chains and trying to track back where it came from. Instead say, when it came out of the ground, that's the last time we knew how much it was. And at this point, I demand that an equal amount of carbon has been taken out of the environment, out of a power plant, and I have that carbon back. You basically cleared the carbon the moment it entered the economy. I don't have to track it through anymore. And at the end of the day, if I'm a bakery, I have no idea how much carbon I consumed either as natural gas in my oven or as electricity. But I do know that any carbon I consumed has been cleared when it came out of the ground. And if I sell you certificates of sequestration and it turns out my supply chain had 2 of them in it, I can't possibly make money. So the bottom line is we need to do that. If we do that, we don't need to trace carbon through the supply chains, which is incredibly difficult. And I would argue the companies like Meta and Microsoft should actually stand up and say, we are in a position maybe to get a rough estimate of what it is, but we should fight back and say the electricity we get better be clean. And you can guarantee it if you do it up front. And that's a lot easier than trying to figure out how much they actually used. And I would argue lastly, and there you see where I see direct air capture, and Peter Eisenberger never liked when I said it, but I say it anyhow. DAC will set the marginal cost for carbon removal, and I actually here qualified it as will likely. If one of you has a technology which is so much cheaper than direct air capture and has the capacity to get scale, then DAC will not play a role. But if all else fails, the last thing I can do with any carbon emitted, I can remove it from the air. And therefore, that will set the marginal cost, unless you didn't need it at all. So therefore, I'm very, very keen on getting that marginal cost down, because if that marginal cost is $100, we are in good shape. If that marginal cost is $1,000, it's only going to be used in an emergency. And how much of it will be used depends on whether it's $30, $100, or $300. And that's the fight we need to fight. And it offers many advantages. It has a very small footprint. A carbon tree, as we think about, is about 1,000 times faster than a natural tree of the same size. Right? It physically and environmentally has a relatively small footprint. And I'm assuming quietly that we get the energy under control. It can be deployed anywhere. Rather than having to sit right next to a populated area and say, by the way, now you're sitting on an awful lot of CO2 right under your house, you could do this in the middle of Australia, right? Or in other places where you are remote. And I think we will need a lot more of it because we are delaying. But the other interesting thing about DAC, and I will close with that, you can not only put the carbon away, but it gives you a chance to get your hands on it. Now think photovoltaic again, and I can turn that carbon back where it came from. And so we don't need fossil fuel in a world which can do that. So if you want to scale up, the time available is very, very short. We are hitting 450 ppm in less than 10 years. I got into it in the very early 90s. Then it was 350. By the time 2000 rolled around and I left Los Alamos for New York City and became a professor at Columbia, it was 370. Then I went to Arizona State in 2014. And shortly thereafter, it crossed 400. And we certainly have touched 430 since. So we are going up right now, nearly 3 ppm a year. So another 20 ppm doesn't take us very much longer. I also put it in one case. We had a 30-ton truck of liquid fuel. I said in around 2014, that's the amount of carbon every person in the world has available. Not annually, forever. That's your budget. Right now, we have cut that down to less than 10 tons. So 2/3 of that truck, which I postulated at the time of Paris, is now empty. This is how far we have moved. As I said, the required scale is formidable. Learning by doing must be dramatic, otherwise we will not get there. And we need to have strategies for scaling up, and I will advocate in the next few minutes for scaling up in a modular way rather than monolithic. And historically, we always were monolithic, because think of refineries, think about power plants. We build gigawatt power plants. On the other hand, it always struck me that a car engine is $10 a kilowatt and a power plant is $1,000 a kilowatt. It depends on the exact nature of the plant, but some turbines are now down to 300-400. But typically a coal plant is right now 1,500-1,600, and a nuclear power plant is like 8,000-9,000. So how come the car engine is 2 orders of magnitude cheaper? And I think that comes from mass production as the big driver. And I would point out, if you come with direct air capture or any of the CDR technologies, you have a real advantage in the way that you have a clean slate. So don't get caught in the old rut and saying we have to do it like we always did. We have a new option, and we can rethink the problem right now, right here. And one of my students, Eric Dahlgren, wrote his thesis on it. And one of the conclusions was the reason we couldn't do that in the past, if you have a machine which makes $10 worth of value, it needs to be fully automated because I can't have an operator. And if that engine size power plant would be replicated 10,000 times to turn into a gigawatt power plant, and it had 10,000 operators, you couldn't pay for them. And the same became clear to me with a mining truck. A mining truck is 400 tons of payload. And it turns out the cost for the drivers in capital equivalent terms is larger than the price of the truck. So you wouldn't want to make it smaller because you squeezed out personnel cost. If, on the other hand, for $5,000, I can refurbish the truck to run by itself, it's far from clear that it wants to be 400 tons. And so I would argue automation has changed this game. So let's think about it that way. The cost of DAC is actually very, very important. I just had a heated debate with my friend, Marco Mazzati, who says, don't think about costs. And I think the bottom line is we actually agree because unfortunately, cost is a very slippery concept. For example, costs today are very different from costs for tomorrow. The other thing is there's a big difference between price and cost, right? But if you think about it for a moment, most of my cost, if I build something, is the price somebody else charged me, right? And so there's a margin built in there. And so it's very, very hard to actually understand what are the real costs and what can be avoided and what cannot be avoided. And I think we all are shocked, and you see political upheaval based around the thing that China showed us that you can do things a lot cheaper than we thought was ever possible. And I think it's unfair to say they are cheating. They just were very good at it. They may also have cheated and done things which were politically not the smartest, but the bottom line is they show that you can do things probably an order of magnitude cheaper than we have figured out. So we need to maximize the odds at the start when we don't really know what the right numbers are. In that sense, Marco is right. Don't hang up on current cost, but figure out how to do it right. So one of the things we learned is if you look at mass production, there is this concept of a learning curve, which basically says the cost has some component which can be learned away, and we added for good measure an irreducible cost, the remainder are, which we think doesn't change no matter how many you make. And then there is this rough rule of thumb, which is an empirical observation, but not theoretically very well understood, which basically says every time you double the cumulative output, the price drops by some factor epsilon, which is typically around 0.8, 0.85, somewhere around there. And you can write that then as a power law. And for historical reasons, I point out you can also write it as n to the log epsilon, because that has the advantage that I can now integrate it and ask, what does it cost to make 1 billion of them? And it turns out if epsilon is 0.8, I have the economies of scale for free. If I simply buy, I have this one machine sitting here and I say, oh, by the way, you need 1 billion of that output. You have two choices. You can make one 1 billion times larger, and then the economies of scale say cost scales like the 2/3 power. This says every time you doubled, you get a factor epsilon. And if I integrate that, the cost of my 1 billion machines also is follow the 2/3 power. So there's no a priori clear cut. And what we learned is sometimes this is faster. So we use that. And then Eric in his thesis pointed out, and this by now has been backed up by other people too, we sorted technologies into large-scale technologies and small-scale technologies, and we looked at the learning rates. And by the way, this graph shows you that there are tons and tons of different technologies which have been analyzed this way. But the important thing is to see the red line for the large thing. It's not learning as well on average. This is the distribution of answers on this plot. And you get 20% learning, that's the 0.8 on small things. It's very hard to get that on large things. And there are a few actually who ended up negative. Nuclear power is in that particular corner. But what happens is small things learn faster. And the other thing is I cheated you, I said all the sum ends up being the same. But what if I just keep doing the last one? I get a lot cheaper. And this is what photovoltaic did. Think about, I'm coming from the future, and I see this friend of engineering friend of mine in the year 1970. And I said, buddy, I live in the 2025. I can tell you that your solar panel, which didn't change all that much, by the way, is now 200 times cheaper than it was right now. So can you please tell me which half cent I'm still paying and what are the 99.5 cents which went away? Even if I were to explain what I just did to this poor engineer in 1970, he has no chance figuring out what's left. And the thing I'm stressing right now, solving this problem is not to have a genius stroke of saying, I fix this problem and then it's all gone. It's exactly like it was there. It's iteration after iteration. In every iteration, you got a little better than you were before. You squeeze something out, you squeeze something else out, and at the end, you were 200 times cheaper, which, by the way, tells you that the irreducible component in solar panels is quite small. And this is not the place where I want to do it, but I'd be happy over a coffee to point out that the irreducible cost of solar, of direct air capture is actually quite small. If you simply say, this is the raw materials I need and I can't get around, and I add all of that up, I'm talking $20 a ton. I'm not saying we can get there. We are now at 1,000. But I'm arguing, just like in the solar case, the floor below which I cannot go is very, very far away. And you see it in the energy consumption argument. Right now, the thermodynamic requirement of direct air capture in every technology out there is a round-off error on the actual energy consumed. So they are really just not good at it. But that's what happens if you start. And that will remain like that unless we get demand. So industries that were forced into modularity often did quite well. I already pointed out the car engine. I couldn't afford a car if it were like a power plant because I couldn't afford parking it in the garage. Right? The interest on my loan would be so high that I couldn't afford it. The smartphone industry I already mentioned. The solar photovoltaic we just discussed. And I put a question mark after wind because wind tried to scale up while making lots of them. And I would argue, and I can't prove that the fact that solar got 24% learning rate and wind only got 14% is tied up in this question that they desperately wanted to get big. And they succeeded, but at a price of learning like a big technology. And as I summarize here, cost reductions are faster in numbering up, risks are reduced, the response to market changes is much more flexible. It's hard to learn in billion-dollar increments because once you lost the first time $1 billion, nobody will give you money anymore. And that might be psychological, but at the end of the day, I also get a lot more iterations if I'm small. And the way I have put this back when we started with Eric, said, assume I'm the chief scientist on your $1 billion project and we are just at ribbon cutting. And foolishly, after I had 2 glasses of champagne, I'm pointing out I now know how to make this brand new plant obsolete because I had a really good idea yesterday. What's going to happen to me? If, on the other hand, we are mass producing these things and I say, I can do this now 20% better than yesterday because I had this really clever idea, the boss will say, do it, and let's do it on the next round. The fear of obsolescence is not the same if you are small and work in increments. It also allows you to test new ideas. If the new one is $10,000, well, if it was a bad idea, I don't do it again. If you set a $1 billion plant in the sand, you think about it twice, right? And therefore, you will not do it in the first place. You don't try out good ideas just because they are too risky. So to go back to the last thing, and I don't want to belabor this graph, but I just want to point out to see the logic how I got there. If I have this learning curve, I need a minimum demand. Think about it this way. I figured out how to do DACA at $700 a ton, and I found some guy with a rich guy with a car, a Rolls Royce, who is willing to pay $700 in order to say, I'm clean. Very tiny market, but I gave it to him. Now that I did this, I'm now only $500. It turns out now I have a bigger market because $500, there are more people. And so the idea is there's a minimum, if the demand, every time let's say 20% is my learning rate, if I drop the cost by 20%, my market better double. And if it does that in demand, then I can run up that learning curve until the very end. And so we need to figure that out, and I would like to turn the order around here. So this graph shows you all these demand curves for 2 assumptions. The red lines are that the irreducible cost is $90 a ton. And the green ones say, I'm an optimist and I can drive it down to $30 a ton. And the family of curves goes at the low end. I have a high learning rate of 20%, lower than photovoltaics. And at the upper end, I have a learning rate of 10%. And here's the bad news. If I have 20% and $30, I can get myself learned out of down to $100 before I have saturated the merchant market for CO2. The US consumes some 7 million tons of CO2 for fire extinguishers, fizzy drinks, all that kind of stuff. If I'm at the good end of that curve, I can get and follow that line. My demand will have barely gone past that before I have gotten down to $100. Or if, on the other hand, you tell me that you have large-scale learning rates of 10% and a high irreducible cost, even the climate market will not get you down. I don't understand learning curves. I'm the first one to admit it, and I've thought about it an awful lot. But you ignore them at your own risk. And we have now reached a point where these technologies better figure out, and let me now get back to the slide. We want a low starting cost, of course, but even more important, we want a high learning rate. And to me, this needs to be modular, right? And the rates vary again across industries and technologies. I'm the first one to admit that we don't know that it will work. For example, we could have an observational bias that only technologies which have good learning rates will succeed, and therefore we haven't seen all the ones who failed, right? And so I can't give you guarantees. On the other hand, I can point to plenty of examples who learned 10 times more. We need to grow at 20%, 1,000-fold, which means we go from the current kilotons a year to megatons a year. We are still 1,000 times smaller than we need to be. But if you give me 10% as a learning rate, then it's a lot harder. Then you end up needing more than 1 million, and that you don't have. So you want a low irreducible cost. And I think it's already time to think about this right now. If you commit to calcium carbonate going to calcium oxide, you just committed to 170 kilojoules of energy, no matter how good you are. Thermodynamically, you needed 20. So I can write the irreducible cost generically, then it's very low. I can pick a particular process and it may get very high. And I should avoid those which are very high, because if I want to come down the learning curve, I'm not very far away from the point where I have to learn it out. And climate change indeed requires 1 million times growth. So we have a lot of runway to make it happen. But I would also argue in winners, and this comes back to the beginning, winners are impossible to predict. We may have a silver bullet, but we have no idea which one of those bullets is just coated in silver and which one is real. So we got to work on lots of things to make it happen. And that, of course, gets better if we operate at that. Now, let me close with something more personal. Eric Dahlgren was a student of mine who worked on this mass production stuff and wrote his thesis in 2013, then went out into industry. And in 2019, months before COVID started, we started to talk on something, and he got all excited. He raised money right before COVID started, and he was lucky. He was looking for a place to do the work, and he couldn't find it before COVID started. Everybody locked down. If he had found the place, he would have been bankrupt because he couldn't have worked. So for a year, he did kitchen science. Because that's all he could do. And then you could, even in New York City, rent space in the garment district where you are commercially and light industry zoned. He got 2 stores on top of a building. And this machine you see in this picture is his first machine. And I'm an advisor to him, so I'm bragging about my student being really successful. He built this machine on top. He's pulling 10 kilograms of CO2 a day if he runs 24/7 through this air capture device, which lives in the top hexagon. It's about year long. And if you want to see the scale on the left side, you see a standard gasoline pump, because inside the thing is a 17-gallon tank. And on the bottom left, looking at it, is the electrochemistry section where he has an electrolyzer producing the CO2 and hydrogen and oxygen, and the CO2 is indirectly produced. Then CO2 and hydrogen meet on the dark side where it's hot in there. You can't look in. There's a micro refinery which first takes the CO2 and hydrogen to methanol, then to dimethyl ether, and from dimethyl ether to gasoline. And then there's a last step to clean it all up. This particular thing runs out of an outlet up on the roof, but it's designed so that it can go up and down with sunshine. And one of the big challenges was to get the capital cost of that electrolyzer low enough that it can sit idle 2/3 of the day. But I think we are on track, and this is the first of a kind. And there's a lot more work and a lot of coming down the learning curve. But I'm really happy to be associated with it, because he really made a difference and got it to work. Thanks so much for your attention. And if there are any questions, I'd be happy to answer.
So there's no roving mic, everybody, so you show off big voices. Please raise your hand and say who you are, where you're from. Klaus, that was absolutely fantastic. And you didn't mention the mechanical tree. If there's no questions, I want you to tell us about the mechanical tree.
Okay, I will. Yes.
How about with Penio out of the US? Klaus, a wonderful talk, and thank you for that perspective. I would postulate that actually batteries, because they're derivative of the automobile sector, and possibly elements of robotics are actually going down that same curve.
I would agree. And an interesting question is, where would we meet? Right now, take an extreme case. I have a simple rule of thumb, because I like to think in rules of thumb and simple things, because fancy models are often no better, because they have lots of accuracy, but in the sense that there are very definite numbers coming out, but then there are lots of assumptions too. So my rough rule of thumb is, if I have $1,000 investment, I need to make a penny an hour. That's 8.7% return. We can argue this is probably before depreciation. So if your battery weighs $1,000, it's 1 penny a kilowatt hour if it has a storage capacity so that it can store 1 kilowatt hour. If it's $200, then it's 0.2 cents. Now, per hour. Now I have to multiply with the time I stored. So my personal view is if you're talking hours, you right now can't beat a battery. If you're talking a year, you are in the tens of dollars per kilowatt hour. So I view this as a spectrum where you have on the short end, you deal with your storage with batteries, maybe flywheels if you get really extreme, and supercapacitors, and all of that lives on that end. And the longer it gets, the more you like chemistry. And hydrogen doesn't store very well, but it's cheaper than making gasoline. But I like that I can, at the end, go to a liquid fuel, which I can store literally for years without much capital expense. And therefore, I can sit on it. And I also can transport it. I realized one day that a 30-ton truck full of gasoline coming down a highway once a day transports 15 megawatts of energy. Right? And I needed to divide the energy in the truck by the seconds in the day. If that truck comes once an hour, which on a big motorway is barely visible, there are lots of trucks in an hour, that's a 360 megawatt power line. I think what you see is the power of redistributing energy in liquid form has an enormous value. You can now go into a desert, a remote desert in the US. Think New Mexico makes in the summer energy which is used at 2 a.m. in the morning in Boston. One of the interesting things is the solar panel on the roof in Boston will make it nearly impossible for that plant I just decided to run 24/7. So we will get lots of peakers which run on fuel, which was made that way. And of course, you have batteries in the mix. There's no question. But here I'm, again, more market-oriented. I'm perfectly happy to say I have no idea how this game will end because there are tiny equilibrium differences which make a huge change in where this ends up. And I can't possibly predict what is the end price of the battery versus the end price of that. So where the boundary between long-term and short-term is, I cannot predict. But the markets will figure that out over time. Did that answer your question?
So when you transform from batteries to stationary to vehicles, and vehicles then to vehicles and grid, in your analogy, you're adding hours to utilization, right? Of the battery within the vehicle.
Yeah.
Which is important to the whole economics.
Yes. I don't disagree, but you still have the battery, and I'm not 100% convinced where this ends up. I think the electromotor is probably the better, and Eric would kill me if he heard me. The electromotor is probably the more suitable form of motive power for a car, although some people really like the engine. Now, Eric would say for the next 10, 12 years, that market is not going to go away anyhow, so this is a moot point. But I like pairwise comparisons, and so assume that the electric car is completely won. And now somebody comes along and says, I have a generator in the back of the car, and your range is now 1,000 miles because I'm converting methanol with a fuel cell or some other way. And the reason you now tell me you can't do it is because the CO2 is in the air. But if this kind of stuff is true, the CO2 is not in the air. So I don't actually know where the market would come out on that. And again, I let the markets figure it out. But we are primed on two things. This is the one. It has to be all electric. Right? And we may or may not be right about that, right? And the other thing where we are primed is because electricity was extremely expensive, it has to go in the grid, the photovoltaic energy. But now that the photovoltaic electricity is extremely cheap, it's not at all clear to me that it wants to go into the grid because the grid is not designed to to hang on to things until they are needed. The grid is there to satisfy instant demand. And I think coming back to the inconvenience thing, if you tell people you can only have it when we tell you, they mutiny, right? So you're much better off to say, we send some power into the grid. And if you want to desalinate water, if you want to make synthetic gasoline, if you want to do 100,000 things which don't need to be running off the grid, then use your photovoltaic electricity directly there. What you then have to live with, whatever technology does that, better be deal with the intermittency. But if I pay 30 cents a kilowatt hour in San Diego, which my daughter pays, and I can have a cent coming out of the photovoltaic panel, I have a lot of room to figure out how to deal with that intermittency. So that's where I live, and I'm perfectly happy to it. And I think we all need to be sometimes more honest that there are a lot of things we can't predict. And if we do that, then we become more flexible, which is not to say we couldn't be a champion of something. And you asked about carbon collect. What I like about that mechanical tree is that it has, first time on a really serious scale, demonstrated that it can take CO2 out of the air in a passive way. But coming back to the irreducible cost, Amanda, on direct air capture, right now the energy consumption of regeneration is where everybody is focused. But you're paying sort of the realm of the coin is the thermodynamic number. Right now I pay 20 coins to get my carbon back, my CO2 back. But I pay 2 or 3 coins on the fans and blowers. And it turns out I'm quite optimistic that 20 can go down to 3 or 4. And now that fan really looks ugly, and that won't get much better because we're already darn good at making blowers and fans, right? So I'm arguing not needing it is actually a powerful thing. And when I started, I realized I can't make the air move faster than 15 meters a second or have the pressure drop, which is equivalent to that, without paying through the nose for blowing air around. But at 5 meters a second, I talk about wind. So the thought then occurred to me, why do we really need blowers? A windmill, we don't blow the air through. That would be self-defeating. But it turns out that big windmill sees far more CO2 in terms of energy equivalent, where I take the heat of combustion, which made the CO2 as the energy equivalent, than it sees kinetic energy. The cubic meter of air has about 20 joules of kinetic energy at typical wind speeds. The heat of combustion, which made an amount of CO2, which is in that same cubic meter of air, is worth 10,000 joules. So it's 500 times larger. And so as a consequence, why do we need to blow the air around if we can just stand there and make it work? And carbon collect demonstrated. But I talked about it last year, so I don't really have to talk about it this year, but there's a whole bunch of things which happened over the last few years. And another piece of good news I saw last night is Climeworks just announced that they got a lot better in the next round. And I want you to think about something about this. Why now? Because suddenly they have competition. People say, well, you can't do it that way. And so they say, well, we figured it out, right? And they need to. And if you only have one company, don't expect learning to lower prices. Auctions come from price discovery. They force price discovery. And if you don't have competitors, the prices stay where they are.